To those of you in Europe, and apologies to those of you in Australia. Welcome to Session 6 of the ESIG 2020 Fall Technical Workshop, being held online on Tuesdays and Thursdays during the month of October and into early November. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As with so many things we were planning to do in person this year, our plans were derailed by the coronavirus, and here we are online again. The workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoiva-san of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who make ESIG what it is, and we encourage you to become involved if you're not already. Regarding logistics, I would ask you to note that the webinar will be an hour long. We'll have 3 individual presentations of approximately 12 minutes each, and we plan to hold the questions for a 15-minute Q&A session after the last speaker. As we're doing with all our webinars now, we'll be using the Slido platform for managing the Q&A. We would ask you to use Slido for your questions, as you will not be able to ask your questions through WebEx. You should go to slido.com on your device and enter ESIG15 as the event code to ask your questions. Please be sure to indicate the person to whom you're addressing the question. The instructions are also in the background slide for the webinar, and you'll be reminded by the session chair. You will see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. So please keep the questions coming during the presentations, and we will address them at the end. Recognizing the limitations of a webinar with typically more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG15 as the event code. Session 6 today deals with a very timely topic, fuels for the future. We will hear several different perspectives on this topic from a U.S., European, and Japanese company point of view. The session will be chaired by Eric Miller of the U.S. Department of Energy, with Bethany Frew of NREL serving as co-chair. Eric serves as the Senior Advisor for the DOE Hydrogen and Fuel Cell Technologies Office within the Office of Energy Efficiency and Renewable Energy, and is internationally recognized for his research on photoelectrochemical hydrogen production. Bethany is another well-known figure in the industry who chairs our Offerings Committee and serves on our Board of Directors. Bethany is a regular contributor to ESIG, and we hope Eric will become one too. Eric and Bethany, we appreciate having you here, and I'll now turn it over to you, Eric.
All right. Thanks, Charlie, and welcome to all. As Charlie mentioned, we have an exciting topic for you today, with distinguished speakers from around the world, and it is my honor and pleasure to introduce them to you. First, we'll hear from Jeffery Preece, who is a Senior Program Manager at the Electric Power Research Institute, also known as EPRI. In this role, Jeffery serves as EPRI's lead on the joint EPRI-GTI Low Carbon Resources Initiative and manages EPRI's research portfolio related to the production, storage, delivery, and use of low-carbon chemical energy carriers. Next up will be Michael Ducker, who is the Vice President of Renewable Fuels in the Western region at Mitsubishi Power, a power generation and energy storage solutions provider in the energy industry. Michael is responsible for overseeing the development and execution of Mitsubishi Power's recently launched Renewable Fuels business, which focuses on delivering carbon-free fuel solutions to the power industry and other end uses. Last but not least, we'll hear from Sikander Mahmood, who is Project Manager in the Future of Gas team at Cadent, leading innovation projects in the gas industry, including High Deploy and High Deploy 2. Cadent is the largest gas distribution network in the UK and the lead network in the High Deploy projects. And with those introductions, let's kick off the presentations with Jeffery.
Thank you, Eric, Charlie, and Bethany. It's a pleasure to be with all of you today. My The topic of the presentation here is focused on really the last 10 to 20% of decarbonization for the electric power sector. Essentially, as we continue to make progress towards decarbonization into the next 20 and 30 years, how will we go that last extra bit to get to full decarbonization, and what do some of those scenarios look like, and what might those challenges be? So when it comes to decarbonization, we can recognize there are many pathways and potential ways to get there. Everything from the source being carbon-free itself, the primary energy perspective, all the way through removing CO2 from the air as those that are already accumulating, or as we continue to accumulate CO2 emissions through ongoing production of electricity and other activities. And then, of course, everywhere in between, looking at the fuel and looking at ways that we can integrate new processes. I'm going to focus mostly on the fuel aspects and their relevance to both the source and some of the opportunities we might find in deploying carbon dioxide removal technologies. So when we think about the way of the future of decarbonization for the electric grid, we certainly recognize at EPRI that there is a strong need and a push to continue producing low carbon power generation. So we will continue to rely on a strong nuclear fleet with license extensions and development of new reactor technologies. We will continue to rely on solar and wind assets to produce electricity with battery storage and also energy efficiency standards being applied, and also looking at ways to directly electrify portions of our economy to enable greater and more widespread decarbonization. We're also considering, and there's a lot of research ongoing at EPRI, focused on carbon capture aspects from our fossil-based assets, especially as they help transition into a more decarbonized future. So with all of these areas, energy efficiency, clean electrification, and efficient electrification, we recognize that we can get to nearly full decarbonization, but it's really considering how do we get that last 10, 20%. And it's not only how do we decarbonize the electricity sector, but we also have to consider other parts of the energy economy that will be challenging to decarbonize. And so there we're looking at core aspects of integration, so looking at systems level analysis that help us tie into where the electricity sector is going and where it could contribute to decarbonization through various pathways beyond direct electrification to enable CO2 emissions reduction now and into mid-century. And that fourth piece of the puzzle and the area that we are focused on, we call low carbon resources. So essentially this is that last 10 to 20% of the power generation grid, but then also it spans into the energy economy as a whole. So if we take a couple of examples and we look at where we might be at in terms of 100% CO2 emissions reduction. In the graph that's shown here, we have a reference case, which is essentially assuming there's no cap for CO2 established, there are no targets for renewable portfolio standards, there are no carbon dioxide removal technologies, natural gas is at $4 per MBTU, and we provided a best case estimate for anticipated technology costs, and then shown where we believe the generation mix for electricity production would be. And then in the 100% cap case, we're showing that the electric sector CO2 emissions are reduced relative to 2005 levels. So what we can find is that there's a lot of assumptions that go into this, and the shorter duration of this talk, I can't get into all of the details, but there is an EPRI report, of course, for reference. But what we find is that there is, without carbon dioxide removal technologies, a need and a role for hydrogen and probably other low carbon resources in achieving final emissions reduction from the electric system. Hydrogen production for the electric sector use in this case would be a power to gas to power cycle. And we see that it actually increases based on various policies, especially those that become more restrictive for decarbonization. But we also have to caveat that there are other aspects at play, other technologies which, based on the long horizon, 30 years is quite a long time, a lot can happen between now and then, that we can see technologies such as batteries becoming more of a breakthrough and then would alter some of these scenarios. So if we look at that 100% cap and we zone in just on the hydrogen portion, Again, this example and these cases based on relative to what we might anticipate for some technology advances being made between now and then, we see that in the 80% scenario, the 80% cap scenario for CO2, there wouldn't be hydrogen production. But then if we go to that last 10 to 20%, we would expect there to be quite a sizable contribution to hydrogen for power generation purposes. And what's interesting for context under this scenario, today the U.S. produces, as of 2019 on an annual basis, approximately 1,300 trillion BTU. So you can see here we're talking about orders of magnitude that seem to be within the realm of possibility, but obviously a lot can change between now and then. And of course, we also have to consider, in this example, we're not taking into account carbon dioxide removal technologies. So what is the value, what is the purpose of CDR? If we look at pathways that could help achieve the limitations established under 2 degrees C targets, what we find is that there are a number of ways, a number of pathways that get us to global net CO2 emissions relevant to that 2 degrees C target. So here on the graph, we're showing net emissions and establishing a curve, which is essentially the curve we are currently on in the trajectory. And we've run a number of analysis based on various scenarios. And in some cases, we can find that if we were to curtail emissions directly, this is global across the board, more than just electric power generation in the U.S., so this is the entire economy. We start to see that there is a potential to achieve net zero at a cost, of course, and this making broad technology assumptions, but there's a pathway to do so. There's also a pathway that if we continue to, on the track that we're on, to continue emitting CO2, and then again, the end goal being to limit to the 2 degrees C scenario, then we have to, in that case, begin to bring the curve down. And the way to bring the curve down is essentially to deploy carbon dioxide removal technologies that physically remove CO2 and store them from being emitted. And in this case, we're looking primarily at bioenergy carbon capture systems, direct air capture, and other similar technologies. So then this paints a picture of an envelope. And of course, within this envelope, there's a myriad of other cases and assumptions. Here we're showing essentially a summary of 408 different model outputs. So the situation obviously isn't very clear, but it helps gives us some perspective for which to analyze the situation. So let's go back and let's look at the same scenario. In this case, we have the 100% cap on CO2, but we incorporate carbon dioxide removal technologies. And on the graph on the left shows the same figure that was shown before. It's looking at generation with no CDR. On the right, what we see is that we have capacity, and we're showing capacity here mainly for interest in this talk because we looked at generation and our model assumptions. There is an uptake in generation from a hydrogen perspective, but it's really where capacity for hydrogen stands out the most in terms of differentiating. So the capacity story is just a little bit more interesting. So the graph on the right, 100% CO2 cap scenario, showing both bioenergy with carbon capture and storage and direct air capture, that's the all category, direct air capture only, so no BECCS, bioenergy, CCS, and then on the far right of that, no CDR at all. And so what we see is that the potential role for hydrogen becomes even more, it grows and becomes even more important as we consider removing those final emissions from the system. So that's the electric sector. And what's really interesting and what we're finding valuable in the context of achieving decarbonization for the electric power industry and for the grid is really that there are other aspects of the economy, other users of energy, other suppliers of energy, such as the natural gas sector, also making very substantial commitments to various CO2 emissions targets by mid-century. And so we're seeing that as primary energy providers and energy suppliers to various end customers and consumers of energy, there also are interconnects that need to be made. And so if we look beyond the potential for electrification, our estimates are somewhere between 40 and 60% of final energy demand will not be serviced by electrification. or will be hard to decarbonize and hard to electrify or expensive. And so then we have to consider other resources, other energy resources, and that's where low carbon fuels and low carbon energy carriers become important. And really it's these, again, these interconnections and the potential to integrate around these technologies and these systems which become critical. And so if we think about from a macro level perspective, where we are moving towards today versus various scenarios which could occur out through 2050. In this scenario, we're calling it transformational. It's essentially showing that there's a 30 to 50% growth in energy due to direct electrification. And then we're showing the opportunity where there are existing energy consumers in a 2050 scenario, which could be served by low carbon resources. And so we see that there is an important balance to both the final energy side, but then also understanding from a primary energy perspective, where we will achieve decarbonization across that spectrum. And how important it is to also be, when we think about the electricity grid and the role that electricity will play in decarbonization, how the infrastructure, how the support could also enable decarbonization across the economy. And so to do that, we're working on evaluating ways that we can begin to continue syncing and connecting the electricity generation and the energy use, both from a consumption standpoint, but also from an energy production standpoint. And that's where we're integrating more research and more opportunities to identify ways that we can deploy hydrogen and bioenergy, upgrade and deploy new infrastructure to support these low carbon resources, and then also find new ways to share the value of these resources across the economy. So our focus through the Low Carbon Resources Initiative is around the entire value chain for these energy carriers. The next two panelists will be speaking on some very specific aspects of these value chains, but essentially it's how are we going to move, and how are we going to use these low carbon resources, and where do we deploy them in a way that achieves affordable, reliable, resilient, low carbon energy for the future across the economy. So I appreciate the opportunity to speak, and look forward to any questions you might have later on. Thanks, Eric.
Great. Thanks, Jeffrey. And as Jeffrey mentioned, we'll be holding questions to the Q&A at the end. So with that, let's move right into Michael's talk.
Good afternoon. So my name is Mike Ducker, and as mentioned, I'm the Vice President of Renewable Fuels for Mitsubishi Power. So today I'm going to talk a bit of what we are seeing in the power industry around green hydrogen in its applications, particularly with our project in Delta, Utah, with the Intermountain Power Agency. So first, briefly, our mission in the Americas is to provide profitable power generation and storage solutions to our customers, empowering them to affordably and reliably combat climate change. We talk about our mission statement predominantly because as we go through the presentation here, and a lot of what Mitsubishi has centered around in our product lineups and our solutions is based on the mission and really helping our customers reliably and affordably combat climate change. And as we look at what's happening right now in the power grid decarbonization, what we've seen to date is really two distinct phases of decarbonization in power. The first one really being the retirement and replacement of coal-fired power plants with a combination of natural gas and renewables. And as of 2005, we've already achieved roughly a 40% reduction in carbon emissions in the power sector just due to this transition alone. But in many parts of the world, and even within our country, particularly in the West, this phase is effectively complete. We've retired almost all or nearly all of our coal-fired power plants, yet the targets to reduce emissions go much further than 40%. We're targeting upwards of 100% in many of these states and regions. So the question becomes, how do we tackle that, achieve those targets of 100% decarbonization, and really look to tackle the long-term intermittency challenges of renewables that currently today are managed by natural gas power generation. So when we look at the opportunities now for green hydrogen and power generation, we really follow four key signposts within the industry. Foremost is regulatory. And so, are there regulatory and legislative environments to promote zero carbon targets. And we're actually seeing this too, not just in state and federal policies, even all the way to corporations who are now requiring that all of their energy over the course of the next several years or several decades be procured by carbon-free resources. That regulatory approach really creates now how do we solve that? And to date, most that's being met by adding an unprecedented amount of renewable energy. And while it's good for ultimately trying to achieve those targets, what we're starting to see happen is the challenge of balancing those renewables. And so as we add more and more renewables onto the grid, we're starting to see more and more need for different types of storage. And already we're seeing the need beyond just lithium-ion batteries and even getting into longer duration forms of energy storage. That gets onto the next aspect of looking at hydrogen, green hydrogen, as a form of long duration energy storage. And I'll talk a bit more about the economics of that. And then lastly is technology to reliably and affordably convert that stored energy back to usable electrical. And this is what we're really seeing today, a lot of our customers pursuing, is the opportunity for gas turbines, which can run on green hydrogen, a form of carbon-free energy, to provide that firm, reliable power at low costs for the power industry. And so we'll talk a bit about the Intermountain Power Project and how they're looking to utilize hydrogen-capable gas turbines to do just that. So when we look at the need for storage, often addressed or looked at is California, given their aggressive targets to decarbonize in a very short time. Right now in California alone, we've seen at just 30% renewable integration, upwards of 300,000 megawatt hours worth of curtailments. And so if you look at the slide on the left, these are curtailments, and two important facts you see is the year on year, we continue to see more and more amounts of curtailments. And so what we're running into is the more renewables we're adding is actually now just creating more and more curtailments. And so how do you balance that so that I'm not having, really this, solar competing against solar? You want solar balanced out over the course of a day and not have it just displacing other solar as we add more to the grid. That's a challenge that's facing right now. The other important conclusion we can draw from the graph on the left is keeping in mind that the seasonal nature of these curtailments, very much prominent there in late winter into the spring months, yet in the summertime we don't quite have the same amount of curtailments. And in fact, what we can, another way to look at this is in California in, say, April, I curtailed 300 gigawatt hours worth of carbon-free energy. And so I was long on energy, yet in August of this year, we had our first rolling blackouts in over 2 decades. So what if I could have stored that excess renewable energy in, say, April and brought it into August when we unfortunately were hitting shortages of energy, and could that have otherwise prevented blackouts from occurring? And again, this is just at 30% today. So if we look on the right, you see where's California headed, and really any state for that matter that has very aggressive decarbonization goals. What we see in a pure 100% renewable scenario is I'm no longer worried about the proverbial duck curve of that, the day-to-day imbalances of energy between daytime and nighttime and that late day peak. I'm actually now more concerned about the seasonal nature of my surpluses and deficits. How do I take excess renewables from one month and transfer it to my deficits in another month? That's really what we're trying to solve now, and this is where hydrogen can play a very important role in that regard. So, a lot of people don't think of hydrogen as a way to store energy, but or think of it as energy storage resource, but that is what it is in the power industry. And when we look at green hydrogen, that derived by renewable energy, it's no different than a battery. And when we look at lithium-ion batteries, where you've got a means to control the charging rate of excess renewables to a form of storable energy, we store that in lithium-ion batteries, and then ultimately when the power is needed, we're converting that stored energy to usable electrical via an inverter, in this case, converting DC to AC. A hydrogen energy storage system is exactly the same type of ecosystem. You've got an electrolyzer technology that really controls your charging rate of excess renewables, converting it to a form of storable energy. We then need a medium to store that energy, and that can be in salt caverns, it can even be in pipelines or above ground pressure vessels. And then when we need that energy, how do you convert that stored chemical energy back to usable electrical? Well, that's where systems like a gas turbine that's hydrogen-enabled or fuel cells can present that opportunity. So again, no different here than a battery. And at the end of the day, hydrogen really much better suited for long-duration energy storage and complements lithium-ion batteries, which are much better geared for short duration. Which gets to the next slide of a study we recently commissioned with E3 Consulting, and they looked at what are the opportunities for hydrogen in a low-carbon future in the West. And really, the two most important things we were able to draw from the study from E3 was, like I just started talking about before, lithium-ion batteries are really ideal for your short duration, 4-hour, 6-hour, maybe up to 8-hour type of discharges, whereas hydrogen is going to be ideal for your much longer durations, getting into the 12, 14 plus hours, and where, as we add more and more renewables, we're seeing that need those longer duration types of challenges that are needed. The other important aspect that we learned from this study was everyone tends to focus on batteries from a discharge of, looking at just, is it a 4-hour or 2-hour or 6-hour? What was important here is how long are you storing that energy? And so in the graph on the right, you can see if I store that for a day, so 0 hours, a week or a month, I have a very different cost profile when I look at hydrogen versus lithium-ion batteries. And so, again, going back to the slide in California, if I want to shift April excess into August shortage, well, lithium-ion batteries are not well suited to be able to store that because they've got auxiliary loads to keep the systems energized. They have, even state of K discharge. Whereas hydrogen, you're effectively bottling it up, and whenever you need it, and given the vast uses for it, it's not facing the same type of round-trip efficiency impacts over that longer-term types of use. So again, we're not here, though, to try to pit that it's batteries versus hydrogen, quite different. They're really solving two different use cases, and both use cases are absolutely paramount if we're going to reliably and affordably try to integrate more and more renewables and help meet our carbon decarbonization goals. So that really draws to the last signpost I talked about was, are there ways, what are the ways we're doing today to really cost effectively convert hydrogen back to usable electricity? And the Intermountain Power Project is really the world's first project geared at doing just that. So just this past year, we were awarded by the Intermountain Power Agency for our hydrogen-capable gas turbines. This power plant is actually an existing coal-fired power plant that will be retired and decommissioned by 2025. And in 2025, we will have gas turbine combined cycles that will be operating initially on a blend of 30% green hydrogen, 70% natural gas. And by 2045, we'll be 100% green hydrogen combined cycle operation. And then the last one, and I'll probably stop here on this slide, wanted to talk about is our Advanced Clean Energy Storage Project, which is actually just adjacent to the Intermountain Power Project. But here, this is where we are, our project, where we partner with Magnum Development, seeking to really create a hydrogen hub in Delta, Utah, to support the West's effort to decarbonize. And this site here, one of our salt caverns, can store upwards of 150,000 megawatt hours worth of renewable energy. And that's really what we see as the great opportunity here in the West to help achieve overall, again, its larger scale efforts to decarbonize. So with that, thank you very much for your time, and I very much look forward to any questions throughout the session.
Great, thanks, Michael. And with that, we'll move right to Mahmood, and then we'll follow that with the Q&A for all the panelists.
Good evening, all. Thank you, Eric. So as Eric said at the beginning, my name is Sikander Mahmood, and I am the project manager in the Future of Gas team within Cadent. So just to give you an overview of the presentation today. So I'll quickly run through the strategy of the gas industry in the UK and how that links into the projects, which I want to go into a bit deeper, which is HyDeploy, looking at blending hydrogen in the natural gas system, and how that fits into the wider picture of a project which we're badging HyNet, and then hopefully take some questions at the end. yeah, as Eric stated at the start of the conference, Cadent is the largest gas distribution network in the UK. We have over 80,000 miles of pipeline, and we also run the dedicated emergency gas line for all the UK distribution networks. So to achieve the target of net zero by 2050, there's a lot of work to do, and the gas industry in the UK has already made some significant strides towards this via the use of biomethane and projects such as BioSNG, which look at converting black bag waste into gas. And then there's the hydrogen blending work that's going on across the world, and that's what I really want to focus on today. And blending hydrogen is there to lead us to progressively start to supply closer to 100% hydrogen to selected consumers, such as heavy industry users, transport fuels, power generation, and new developments. So what is HyDeploy? So it's a project which is funded by the Innovation Programme in the UK. It's led by Cadent as the lead gas distribution network, and we're partnered with Northern Gas Networks, who are the other GDN. We're also working with Keele University, who are the host site, the Health and Safety Executive Science Division, who are providing us with the evidence that we need to go forward, ITM Power, who provide us with the electrolyzer, and Progressive Energy, who are covering the overall project management. So the objective of HyDeploy is to essentially demonstrate that we can blend up to 20% volume of hydrogen within the current gas infrastructure that we have in the UK, and that it can be distributed safely and efficiently with minimal disruption to consumers. And there's a chance to have a saving of around 120 million tonnes of CO2 cumulatively by 2050. And why blend and not jump straight to 100%? I mean, blending allows us to start to hit that decarbonisation milestone with minimal change to the consumers. So the consumers would not need to change the appliances in your homes. The assets that we have in the networks can remain the same. And so there would be minimal disruption. And we can start to really build on that hydrogen supply chain whilst we work towards progressively supplying 100% hydrogen. And it really gives us a chance to reduce the carbon emissions in the meantime, and it's a great stepping stone. And we've used this figure here. It's like taking around 2.5 million cars off the road if we were to blend across the UK. So just to give you an idea of the project timeline itself, we started working on the safety case for the first demonstration project at Keele University in 2017. We are still blending at Keele University. Due to COVID-19, we had a short break. However, we have extended the demonstration, which should hope to finalise in March 2021. And in the meantime, we've been developing the evidence for the safety case for the second public demonstration of hydrogen blending, which will be in the northeast of England in a village called Winlayton. And we're hoping in the next few months we should be on site and ready to blend. And once that's up and running, we will start to develop the safety case for the final demonstration, which is part of the HyDeploy 2 programme, which will be a public demonstration in the northwest of England, and that will hopefully eventually lead us to roll out of hydrogen blending across the UK. So Keele University is a perfect location to have a first-of-the-kind trial. It's really like a small town on gas. There's around 100 residential properties that we're testing on, a few multi-residential buildings and some office blocks and commercial buildings. And it's been really good to work with Keele because, in essence, you're working with a private gas distribution network and having to deal with one party rather than multiple parties. And really, it's like a living laboratory. So I spoke about the safety case, but what does that actually mean, and what does building the safety case actually mean? So there's a lot of work that goes into gathering the evidence. The current UK gas safety management regulations state that you can only have 0.1% hydrogen in the gas networks. So to be able to blend into these trial areas, we need to achieve an exemption to those GSMR regulations, which will allow us to have up to 20%. And to do that, we need to build a safety case of evidence. So we've been conducting some research on the appliances that we have on the networks, the boilers, the gas fires, etc., and doing laboratory tests on blended gas and natural gas. The same goes for the materials that we have on the Keele network and the northeast, reviewing those pipelines and the assets that we're going to put the blend through, and doing some tests in the laboratories. We're also looking at the gas characteristics. So how does gas accumulate in a building, and how does that differ for blended gas? And what are the consequences of that if it was to ignite? And then there's the operational side, so looking at the gas detection equipment that we use currently, and how will that work with blended gas, and also the operational procedures that we have for emergency response. And then finally, and quite importantly, is the customer perception piece. So HyDeploy is the first time we've had blended gas in a network in the UK, so we've been able to gather some real evidence on the customer perception side, working closely with the customers at Kiel and in the Northeast. And all that leads us to gathering that pre-trial work evidence to achieve that exemption. So following an exemption, we then start the installation phase on site. A few of these pictures show the equipment that we're installing on site at Kiel University and some testing that we did beforehand. On the next slide, I'll go through the setup on site. So we have a medium pressure gas pipe running from the gas network into this compound, which you can see on here. So where it says natural gas inlet, that's coming in to what's labelled as the hydrogen grid entry unit. We're producing the hydrogen on site via the electrolyzer using electrolysis, so splitting water into hydrogen and oxygen. The hydrogen is then stored in what you can see labelled as the buffer tank, and then injected into the hydrogen grid entry unit where it mixes with the methane. That then goes around the volume loop to ensure that the gas quality is of the right standard and the right specification, and then that's going through the blended gas outlet into the local pressure reduction station that we have to bring it down to low pressure in the network. And that's essentially the layout of the compound. In terms of where we're at now, so it's fully built. As I said, we are running on site at Kiel University now. We did have a short delay due to the fact of COVID-19. However, we have extended the trial until March 2021 to give us that extension to allow us to gather a little more evidence on blended gas. Simultaneously to the work that we're doing in the domestic properties and the commercial properties, we are running a boiler house experiment on site. So we have 8 boilers installed, and 4 are running on blended gas, 4 on natural gas. They will then be compared at the end of the trial, and we have them running on longer cycles to give us years worth of data. We'll then send the boilers back to the manufacturers and really ask them which one did you think was running on blended gas and which one was on natural gas. And then allow them to dig into the details and the components to see if there was any long life impact. So in terms of summary today on site, there haven't been any issues reported with the appliances that we have in the homes. There haven't been many issues reported on the network, other than the usual business as usual gas emergency reports. In terms of the gas demand on site, that has been more variable than expected, which we didn't know in the beginning, but we have been doing some work on that. And you can imagine it's a first of a kind project, so you are going to have these issues and things that you need to resolve. And like I said, it's the first time the UK have managed to engage with regards to hydrogen on a real gas network, so it's provided us with some great learning going forward. So that leads me nicely onto HyDeploy 2, which is the public demonstrations. So I mentioned at the start the Northeast demonstration and the Northwest, and those are encompassed within HyDeploy 2. It's the same project consortium so that we're able to carry on with the learning, and the objective is very much the same. However, the outcome is the fact that following HyDeploy 2, we should be in a position for UK rollout of blended gas. So a supplier is able to apply and inject hydrogen into the gas distribution system, just as biomethane producers can. So in terms of the trial principles themselves, at Kiel University, we aim to do 100% gas safe checks on the properties and also do some bottle testing. So putting bottled mixtures of hydrogen and natural gas into each property and each appliance. However, that's not a feasible position for rollout of UK-wide. Therefore, on the second public trial, we have aimed to do, again, 100% gas safe checks. However, we've limited the bottle testing. We've gone to no bottle testing. And then in the second public trial in the Northwest, we will do a limited amount of gas safe checks and 0 bottle testing to allow us to slowly reduce the mitigation, because it wouldn't be feasible to go into millions of properties and check each appliance. So just to give you an overview of the location in the Northeast, So we are injecting into Winlaton, which has around 670 properties. The arrow that you can see on the bottom is where the compound will be placed. And there will be a medium pressure line going into the network and blending into that isolated network. So the current status of the overall project, the exemption for the Northeast project is under review via the Health and Safety Executive in the UK. Once we get the exemption approved, that's when we will be able to start the live trial in the Northeast. The compound is currently in the design and install stage, which will be ready in the next few months. And we are really embodying the learning that we've got from Keele University and from the evidence that we've been gathering going forward and working towards closing those evidence gaps. So finally, just to put this slide up as a vision for the northwest of England in the UK, and from Cadent's perspective, this is what our HyNet project would look like, where you have a central production of hydrogen via methane reforming. The carbon would then be captured, and you can see that on the orange pipeline, and stored at sea. The black pipelines indicate the 100% hydrogen being distributed to the selected consumers. And it just shows you how crucial a hydrogen blend will be in this sort of system, where we'll be able to tap into that 100% hydrogen mixture and blend into millions of customers in the domestic setting and also the industrial setting going forward. So thank you very much. I'm happy to take some questions at the end. I think that'll be fairly soon.
Great, thanks, Sikander. That was a great presentation, and thanks to all the presenters. We're getting a lot of questions in, and I think I'll hand it over to Bethany to start moderating the Q&A session.
Thanks, Eric. And thanks to all the speakers. Yeah, we have a lot of questions here. There seem to be some common themes, so I'm going to try to work through the voting, which I guess I'll encourage all the attendees, if you like some of the questions that are already written, go ahead and give this a thumbs up, and that'll push it to the top of the stack.
And Bethany, before you go on, I think we can show the screens for our panelists if they want to put their videos on and keep on mute until it's active. Yeah. Thank you.
Yeah, thanks, Eric. That's right. Great. So there were several questions. We'll start with this one at the top, but there were several others that were related to really kind of the blending element. So when you have a certain portion of hydrogen, a certain portion of gas, how does that affect the heat content? How does that affect emissions? There were other questions, I think, that related to efficiency as well, or other sort of downstream impacts. So I guess that's really directed at any of the speakers, but maybe Sikander or Mike, you might be best positioned to answer those given the topics that you presented on.
Yeah, absolutely. I can give that a go. I mean, in terms of the work that we're doing with HyDeploy, so we are only looking at a blend of up to 20% hydrogen, and from the evidence and the research that we've been doing, that we have seen minimal impact in comparison to natural gas. As you do increase the hydrogen percentage past 20%, yes, you will start to see some changes in the flame picture, in the heat profile, and the operation of the current appliances that we have on the networks, which is why we have put the 20% as a hard stop. If you were to blend over that, you would need to start to replace the assets that you have in the networks, and therefore 20% is a great position to be in, and whilst we start to work towards the 100% goal of hydrogen.
Do you have any comments on the emissions impact? I guess this question here at the top, the hydrogen only has 20% of the heat content by volume of versus gas. Does that mean blending? Yeah.
Absolutely. I mean, we appreciate it's not going to tackle net zero straight away, and it's a stepping stone to decarbonize. As I said in the beginning, if you were to blend hydrogen into the network across the UK, it'd be like taking 2.5 million cars off the road. So there is still a chance to have a significant impact on decarbonisation. As you can imagine, adding hydrogen into the gas mixture would also reduce the carbon monoxide content, reducing the risk of CO fatalities.
Great,
this is Jeffrey. I could add, I think we have to remember that we're talking about a transition. We're not talking about flipping a switch and going right to hydrogen or low carbon resources tomorrow. And so what that means from an economics perspective is we have assets, and certainly, Sikander's company has a lot of assets that are on the ground that have book value still. And so part of this is how do we balance the affordability aspects of achieving net zero, and where are the technology advancements that are needed, because it's more than just the pipeline. In this case, it's the valves, it's the stations, it's the homes, it's the people who have to agree that this is something that they're signing up for. And so we have to pay close attention to all of the decision-making that goes about as we transition further and further. Get people comfortable, get the equipment aligned from an affordability, reliability standpoint as we start to move and make progress into decarbonization.
Great, thanks, guys. So I want to call out Mike, because there were some other questions. They're not at the very top here, but they're kind of related to this idea of blending. And I think specifically there were some questions on the turbines and the gas turbines and the modifications that are needed to make those compatible. And so, Mike, I don't know if you could maybe just talk to that point a little bit more. I'm trying to remember some of the questions. Yeah, just I guess the timeline that's required. I think you gave 2045 as kind of the end point. Why does it take? Why are you estimating that it'll take so long to get to that point?
It's a great question, and
yeah.
And to be clear, that's what the regulatory requirements are for that specific project. We will have 100% capability by 2025. So this is not something that we're waiting 20 plus years to pursue. The regulatory requirement is a 2045. Again, I go back to this concept of hydrogen as an energy storage resource. And the fact of the matter is, today, if I had 100% capable hydrogen-capable gas turbine, that's a gigawatt. That's basically a gigawatt-sized battery. There are no gigawatt lithium-ion batteries. The entire installed base of lithium-ion batteries in the United States is a gigawatt. It's about a gigawatt and gigawatt hour. So one power plant running 100% would be the entire United States equivalent of batteries. So let's keep that in context when we think about green hydrogen, and people see, oh, it's only 30%, or why are we doing this? It's exactly what Jeffrey was talking about. It's a transition. And so what do we need in 2025? 30% will be one of the largest effectively energy storage systems in the entire U.S. for that power plant, just running on a 30% blend of hydrogen. And again, one of the best attributes of the gas turbine is we can effectively, over time, as more and more renewables come on, we see more and more curtailments and more need to add hydrogen. We're just effectively increasing the amount of hydrogen content in that unit. We're not adding a bunch of new batteries. We're not adding a bunch of new infrastructure. It's really making use as cost effectively as it can to transition that unit to a fully decarbonized unit over time. And in the West, maybe that occurs much quicker and at a rapid pace, and where you hit 100% hydrogen needs at an earlier date than just other parts of the U.S. potentially. But nevertheless, that's what we're really positioning these units for.
Hey, Bethany, can I just follow on question to that? To all the panelists. I think it's really important that we're looking at this now, because not only is there combustion differences in burning hydrogen or blends of hydrogen, there's also the foundational materials compatibility of the entire infrastructure, if it's turbines or pipelines or anything. I think there's a lot of work. Well, I know there's a lot of work going on in this area at the department. I was wondering if the panelists could comment on how they see that aligning with the future plans in terms of solving all of the challenges in those areas.
I can address, foremost from our IPP, the project with Intermountain Power Agency. Keep in mind, we have guaranteed the operation on hydrogen. So how we're installing the infrastructure, what we're doing up front is making sure that over time it can convert to 100% hydrogen. So what does that mean? Physically, what's changing? We've got some bigger enclosures. We've got some bigger pipes and some bigger valves. We've got additional fuel flow meters. I mean, there's equipment like that, but what we're talking about is not some step change in cost. I mean, these are effectively incremental cost changes. Like I said, we're talking flow meters and different sizing of piping. It is necessary. Now, if you don't do that up front, it doesn't preclude you from doing it 10, 15, 20 years from now. It's just going to make it a bit more expensive than if you design these units up front. So what we're telling all of our customers today is design it up front in mind that I'm going to need to be 100% hydrogen ready at some point in the future, whether it's 10 years from now, 15 years from 20. And, when that moment comes in time where I want to, again, increase beyond certain thresholds, then you've, pre-designed that site with that in mind, and it's really minimal changes that we need to do in order to get you there to 100%. So that's really what we've been tackling, that not just with, again, this is a contracted order with the Intermountain Power Agency. All the conversations we're having with customers today really get around that aspect. Again, this whole 100% enabled concept is really taking wind in that regard.
Great.
Thank you. Thank you, Michael. There were several questions that were hinting at what exactly are you doing to modify these plants? So I think those examples you just gave were really helpful in giving the audience a better picture of what that transition looks like physically. There were also several questions that relate to the top one that's shown on the screen here that is really getting at the economic justification for why hydrogen. And so I think this can apply to all three of the speakers, so maybe we'll give each of you guys a chance to comment on this. How are you justifying this transition to include hydrogen? Is it actually cost competitive, either from pure economics, or is there some sort of efficiency benefit that we're gaining? So if you guys could just comment on hitting some of those highlights there, I think that would help to answer several questions.
So from EPRI's perspective, I know I went through pretty quickly some modeling scenario analysis, but we're finding there's a lot that comes to play. It's technology advancement. So where will electrolyzers connected to the grid be in 30 years from now? Will we and how will we be able to achieve $2 or so per kilogram from a grid connected or a nuclear connected electrolysis production system? Where will storage and delivery costs go? Can we use existing infrastructure? Will we be designing and laying new pipeline and new equipment to support it? So there's a ton of questions and different caveats that we can take. Our approach has been looking at the value, looking at the cost, looking at performance standards, projecting out based on our R&D activities and those globally, and then trying to understand the balance with other technologies. Because at the end of the day, for the grid, for the economy as a whole, optionality will be critical. And that's why we see the story should also include more than hydrogen, because hydrogen could be an energy carrier for ammonia, for synthetic methane. There's also biofuels and the role that they will play. Renewable natural gas could be incorporated into the transition to decarbonization. So as we think about the myriad of options that go forward, there's also, beyond technology, there's policy, regulations, all these other things that influence costs more than just the direct technology. So we try to incorporate a lot of those to the best that we can project out that far. And part of our research in this 5-year initiative is really honing in on those technologies and finding applications for hydrogen that allow some of the early adopters to help drive the market forward.
And here's what I'd say just very quickly on this question. When people ask us this question too, when we're talking about the power industry, dollar per kilogram means it's a fuel. And as everything I talked about in my presentation, we really view green hydrogen as an energy storage resource. So what I asked back there is, what's the dollar per kilogram cost of lithium-ion batteries? What's the dollar per kilogram cost of pumped hydro? Nobody asks these questions because it doesn't make sense. We're not solving a fuel challenge. We're solving a storage challenge. And so the better question to ask is, what's your dollar per kilowatt hour cost? And how does that, relate to the overall integration of short duration, long duration energy storage? And how do I get towards a low cost, high reliability, carbon-free grid? And that's really our focus here when we think about hydrogen. And the only other thing I guess I'd say that too is, again, going back to the slides I showed, what's the value of having a resource that could have prevented a blackout that occurred here back in August? And as we continue to add more and more renewables, that challenge is certainly going to continue to grow, where we have these mismatches between seasons. And it really is a challenge I think grid operators and long-term resource planners are trying to get their head around of how do I value short duration batteries, medium duration batteries, long duration batteries. But that is what we need to solve that question, and the most cost effective way to integrate. And all that gets back to, again, what are you trying to solve here? Well, it's carbon free generation that is being targeted within these grids. So,
and just to quickly add to that, Bethany, we know that the road to decarbonisation is going to cost more money, but it's about evaluating the options that we have. I mean, Cadent has around 11 million customers, and the user base is diverse, and the transport and heat industry is really complex. So it's about providing those options and the availability for public choice. And the route to decarbonisation can be simpler if we're going through blended gas and eventually through 100% hydrogen. And there's aspects such as what Michael alluded to in terms of seasonal demand, and we've had seasons here in the UK where you have the beast of the east, where you've had snowfall for large periods of time where people want to flick on their heating and it to work straight away. So those sort of occasions is where hydrogen really comes into play, and long-haul transport and heavy industry users such as glass manufacturers. And it's really key to understand that diverse user base.
And Bethany, can I follow up on that as well?
Yeah.
Okay,
Yeah.
Thanks all, and thanks all for giving such a clear description of our H2 at Scale initiative. It's really exciting to hear. But what I will add that I think Jeffrey mentioned in his presentation he kind of used the terminology make, move, and use, and I think it's important to realize that that there's a combination and cost trade-offs amongst that, and it depends on the end use. If you're doing it for storage or for large-scale energy transport, and all of these things are promising that they also be taken into account. Maybe everyone could comment a little bit. I think, for example, the large-scale transport of energy from Australia to Japan is something in the works. People are looking at liquid hydrogen as one carrier, possibly ammonia as one carrier. But all of these factors come to play. I'm wondering if you've thought about those trade-offs, whether that be synthetic methanol or ammonia or hydrogen. I know it's a big trade setting. It's a big question, but I just wondered if we could get the panelists' thoughts on how they evaluate those various options.
I can say it's definitely in our portfolio to be analyzed further. We're working very closely with a lot of major players in the energy space, not directly tied to electric and gas utilities, because as was mentioned before, there is a significant portion of the energy economy which will rely on alternatives to electricity as a clean energy source. And understanding the value that they place on fuels or energy carriers and the options that they wish to maintain in terms of availability and reliability will all derive much more important insight than simply looking at efficiency. So we certainly recognize that a power to gas to power from an efficiency standpoint doesn't look very good. But when we think about all of the other value components to such a scenario, as Mike has pointed out and Sikander has pointed out from a grid perspective, it's more complicated than what we see on the surface. And so we have to take into account the full aspect of economy-wide decarbonization. That's really our focus.
Great. Thanks.
Yeah, and I want to build on this idea sort of these different end uses, because I think this captures another kind of set of questions that have been coming through here, talking about what will happen if we have a lot of vehicles that are made with hydrogen, that are hydrogen fueled. I think that one was directed at Sikander. But also sort of just this idea of the infrastructure that's needed to support all of those different end uses. And so if the speakers could maybe talk about some of those just different aspects of different end uses and how there might be additional development that's needed to support those, and what sort of outlook you see. I guess, electrification of load was another set of questions that came in, because that was a key kind of pillar. I know in Jeff's talk, he talked about electrification, and it was a theme throughout. How do you see new loads coming in? Do you think they're going to be able to support the different profiles that make all of this, all of these different plans that the speakers talked about possible? I kind of covered a lot of items, but maybe the speakers could hit the ones that were most applicable.
Just to touch on your first point then, Bethany, with regards to transport, I mean, we do understand that as hydrogen develops further, there will be more vehicles, trains, buses, trucks, etc., that will be ready for hydrogen. And it's important that us as a gas network are ready for that change also. So we do, in Cadent, we do have a portfolio of projects with regards to transport, which we are working on, looking into how hydrogen will be feasible for trains. We've got projects with the National Physical Laboratory assessing if we are able to extract hydrogen from the gas distribution networks. Is it pure enough to be used with fuel cells? And we've got various projects looking at the impact of hydrogen on CNG trucks. And it's about gathering that evidence base to really understand that we're able to support the upcoming demand that we will potentially have.
What I'd add to that question is, I think one of the great opportunities here is when we look at even just running on partial fractions of hydrogen in the gas turbine, we're talking upwards 100 tons per day, type of demand at the percentages, the lower percentages I talked about. Whereas, what we're looking at for vehicle infrastructure, some of the fueling stations they talked about is maybe, a couple tons per day. So the benefit here is the power industry really can represent that opportunity to get scale, more centralized type of infrastructure. And then as we look at some of the other industries like, heavy haul transport, how do they start decarbonizing and utilizing hydrogen, being much smaller demands, they can, effectively piggyback off of the types of scaling and cost downs that we're going to achieve in the power industry. So I think that's what's really exciting here is that, the type of scale and what we're doing here in power really transcends the opportunity beyond just decarbonizing power. It really is going to help leverage many of these other industries as well. And basically the analogy I give is, vehicles and consumer electronics did for batteries what they ultimately did for the power industry. Power industry basically piggybacked off that. I actually think it's going to be reversed for hydrogen, is that hydrogen is going to be the one that gets the cost downs, and then, they're going to be the beneficiaries, the, transportation sector and other industries from there.
All right. And unless we have a final comment on that from Jeffrey, I think we're running out of time and we'll need to wrap up. So Jeffrey, any last thoughts?
I'll pass. Thank you.
All right, sounds good.
Hey, Eric, can I actually, I just want to say really quick, because there are a couple of points I think that you actually raised, like the exporting from Australia to Japan. There was a session a week ago that was on October 8th, hydrogen production and flexibility requirements. Had some great presentations there. So if anyone's really interested in this topic and missed that session, you can go back to the ESIG website and catch that. It's available to watch the recording and see the slides. So just wanted to highlight that.
Thanks, Bethany. And thanks to all. I'd like to thank our panelists for their great presentations and the discussion today, and thank all of you for your participation. This has provided a really good update on the global outlook for the future role of hydrogen, and I hope it has provided some stimulating thoughts for everyone. I'd like at last to remind you that there are 6 more technical sessions that will be held during the remainder of the month and into early November. You can find the full schedule of the upcoming sessions on the ESIG website, and you're all invited to attend. The next session on interregional transmission will be held next Tuesday at 2 p.m. Eastern Time. And I thank you again for your participation. Stay safe, and we look forward to seeing you next time. So long.